All right, if you do not have any questions, I'm gonna just finish 4.4, which we stopped part of a 4.4. So let's finish 4.4. So the part we're gonna do is a mean value theorem for integrals. Okay, mean, what's a mean mean to you? Mean means what? Average, right? Where the average is. So it's a mean value theorem means I can find the average height and I multiply by the width. It gives me a rectangular area. The rectangular area will be sufficiently close to the real area of under the curve. That's what mean value theorem means. So this is a good picture. You can see it. So look at this. This is a perfect picture that I want you to look at it. So we are looking for area under the curve. So this is area. The true area is, I'm gonna use a blue. Okay, the true area is this. All right, that what I highlighted with blue. But I want to find this area using a rectangular shape, okay? Because we know how to find area of a rectangle, right? Area of rectangle is a base times, this case the base is this. That's my width. All right, so area of a rectangle is always what? Width times length, or I can say width times height, okay, whichever, they're the same thing, okay? So what I'm gonna do is, okay, if that's true, then I know what to do. How about we found the average height, okay? So average height, in this case, is right here. That is f of c. It's average height. Or you can say length. All right. So I can find my area under the curve by multiplying the width times the height. That's my height. That's my height. That's my width. Okay, so that gives me, that's my width. My height is f of c. Because this height right here, this height is happen to be middle. Okay, in this case. All right, so average height times the width gives me an area of that curve. Okay, that's what it is right here. So does everybody understand the concept? The mean value theorem for integral means you find the average height and multiply by width, give you the rectangular shape. That is your mean value theorem. So in other words, you can think of, I can find integral of the area under the curve by finding a mean value theorem, which means multiplying by the height and multiplying by width, which gives me a rectangular shape. Hey, Ethan, I'm in trouble because I forgot to bring a connector. So there's nothing to show. Sorry about that. Okay. Let's just see. So f of c. So you can think of this is my f of c, and that's my b minus a. So that's how you get your area. Okay. So you can find your area under the curve by finding a width, which is b minus a, times height, which is f of c. The c is happen to be, in this case, is a middle number, okay? But it's not always true. For this case, we're gonna use that one, okay? So you can also set average value of a function. All right, the average value of function means that's the one that we just did. This one right here, that's average. Okay, it's average value. Because remember, this is a height that we chose. This is a height, which is average height. Okay, so in other words, average value right here, and when they come over here, say average value of a function, this really means asking you to find f of c. That's equivalent. Okay, so then we can say, okay, in other words, this is what we know. Remember, a of b, f of c, that is equal to f of c times b minus a. We know that from mean value theorem. So if I'm looking for this, the average height or average value, what would you do? You can divide everything by what? B minus a. Okay, then you cancel that out. So you have this f of c, which is average height, the average height, or you can say average value of a function. That's the same meaning, okay? Average value of a function, which is average height, is the same as the integral divided by a b minus a. Okay, does everybody see how you got this one? This is equivalent to what we were doing before, mean value theorem. So it's average value of a function came from mean value theorem, which is average height, which is f of c. All right, so again, when you have a curve, you can find this area under the curve by finding an average function, average value of a function times base b minus a. All right. All right, so we don't have to worry about that part. Okay, so if they're asking you, this is a question right here. Find an average value of f of x equal to 3x squared minus 2x on the interval 1, 4. Then what would you do? You just use our formula. So b minus a, which is equal to 4 minus 1, which is 3. So you get this number right here is the same as 1/3. And f of x, which is right here, 3x squared minus 2x, which gives me 1/3, 1/4. Okay, let's do, so that gives me 1/3, and then I'm gonna have 3x squared, 2 plus 1 divided by 2 plus 1 minus 2x, 1 plus 1 divided by 1 plus 1. Or then you can clearly see 2 plus 1 is the same as 3. 2 plus 1 is a 3. Okay, so you can see it. 3 and 3 cancel out just to this. 2 and 2 cancel out just to have that. All right, now, this is the best time to use Julia, right? Because you can just plug it in and you get the answer. For whatever the reason you decide not to, then you're gonna do 1/3. 4 to the third minus 4 to the square minus 1/3. 1 to the third minus 1 to the square. All right, when you do this, obviously this is equal to 0. So whatever that is, that will be your answer then, right? 4 to the third minus that will be what? 4 to the third is 64 minus 16, which give you 1/3. Taking away 16. So this is a thing that I really like to just use Julia, so you don't have to simply add and subtract by yourself. So 48. So that's the same as what then? 16. So that's your answer right here. All right. So they're telling you your graph looks like that. But when you find the average, okay, so this is what you get. Your average height right here, the average height is 16. So if you do 16 times 4 minus 1, which is 16 times 3, give you what? 48. So that is area under the curve. Because I can draw myself a rectangle right here. This is just 16, that's a 3. So 3 times 16 give you area under the curve, which is same as a rectangle. You know how to find the area of a rectangle. So 16 is average height. Or you can say average value of a function. If they're asking you to find the area under the curve, what would you do? You just multiply by f of what? F of c times b minus a, which is 16 times 4 minus 1, which is 16 times 3, which gives you 48. Okay, so now let's moving on to a different one. So all those four, so far, we were doing a fundamental theorem of calculus, like the first fundamental theorem of calculus. Now we're going to look into the second fundamental theorem of calculus. So this is a new. So earlier we saw that the definite integral of f, or the interval from a to b, was defined using a constant b as the upper limit in integration and x as the variable integration. Okay, now, but we're going to change it. However, a slightly different situation may arise in which a variable x is used in upper limit of integration. So we're going to change a variables now. Okay, so we're not going to be confused with the variable as upper limit and then function as x. So we're going to introduce a new variable called t. Okay, so far we've been doing this. Okay, definite integrals using a first fundamental theorem of calculus. This is what we use. We use constant as lower limit and constant as upper limit, and my function has f of x. X as my, this function is defined by x. But now the second fundamental theorem of calculus, it's changed, okay? So now the upper limit is not a constant, but the upper limit is become a function of x. All right, so because of that, I want to introduce a new variable called t. It doesn't have to be t, but I can call it, if I want, I can call it g, or like s. I can call any variable, okay, but I decide to call t because that's the thing that we usually use. So now the inside the integrals, we have integrand function, we call it f of t dt. But the lower limit is still same as a constant. So let me introduce you. Let me tell you why this second fundamental theorem of calculus is important. Okay, so say I want to evaluate upper limit as 0, pi over 6, pi over 4, pi over 3, and pi over 2. I want to do different upper limit as you see over here. I want to have different upper limit because I want to know what's my area when my upper limit is only 0 to 0, or from 0 to pi over 6, 0 to pi over 4, or 0 to pi over 3, 0 to pi over 2. I want to know, okay? I want to know what that equal to. So which means my x is changing each time. So first one, x is equal to 0. Next one is x is equal to pi over 6. Next one, x is equal to pi over 4. I'm doing a different one. So in other words, I'm accumulating my function. So when you take antiderivative of a cosine t, that is equal to sine, okay? So sine t. So you integrate, so you plug it in, upper limit as x, which you get sine x, lower limit as 0, sine 0, you get sine x, okay? No problem, sine x, great. Now, I don't have to take integrals again and again and again because I got my answer, which is x sine x is my answer. So I can just replace x as a 0, x as a pi over 6, x as a pi over 4. So when sine, this is a sine of a 0, which gives me 0. So I don't have any area. That's why you don't have any shade. Next one, when I have sine of pi over 6, that gives me 1/2. So I have an area right here, which is only 1/2. Okay, what about the next one? So I want to do sine of pi over 4, which gives me square root of 2 over 2, which is I have a little more area. But did you notice that I'm not taking integrals again and again and again because I had this. And then I found that to be sine x. So my x can keep change depending on what the variable that I chose. All right, very first x, I chose x to be 0. Next one I chose to be pi over 6. Next one I chose to be pi over 4. Now I'm gonna choose to be pi over 3, which gives me sine pi of 3 gives me square root of 3 over 2. So a little more area. Now I want to choose sine of pi over 2, which gives me 1. So entire this quarter circle is my area. Okay. So did you notice that I don't have to do this? I don't have to do this. Every one of them. Okay, you notice that I had to do 1, 2, 3, 4, 5 of them. See, I have to do 5 integrations. You know what? I didn't have to do it because I used my upper limit to be x. So I changed my x to be different number. So I only did one time. Okay, only one integration job gives me 5 different answers that I need. You notice that? That's why second fundamental theorem of calculus is important. It gives you accumulations. Okay, you can change upper bound with a different number by using a variable instead of a specific number. Because if you use a specific number, you have to find integral for every one of them. All right, it takes a lot more time. You have to do 5 integration, but you replace that with a 1 integration problem by using a second fundamental theorem of calculus using the upper limit to be x. Does everybody see why second fundamental theorem of calculus is amazing? All right, because you just reduce 5 integration work into the only 1 integration work. So for now, so I'm gonna say, okay, let me tell you even more amazing thing is. So example 6 noted that derivative of derivative of f is original integrand with only variable change. That is, so if I have this, the derivative of f of x, so f of x, you can think of the original function. All right, which is what? Sine x. Remember that we found that when you take derivative of x over cosine t and dt, you find to be what? Sine x. So the sine x, I will call it original function. The original function, you usually use capital letter, okay? So you will remember now we're not just doing a derivative, but we're also doing an integration. So we're trying to distinguish between the regular, the f prime, and then with the original function. So we are introducing capital F to be an original function, okay? The one that you take integrand to become the original function going up, you call it f of x, okay? So my f of x, the given problem is sine x. Yes, we got that. Now, so what we know is derivative of a sine x, okay, which is give you what? Cosine, right? You know that. So now this is what we know. So if I do derivative of an integral, it's kind of like you are what? Canceling. You're taking a derivative, you're taking a what? Integrand. Remember, derivative of an integrand is what? They're opposite, right? Integral is, in other words, antiderivative. So derivative to antiderivative, what happened? They cannot cancel out, isn't it? They cancel out. So you just come with a cosine x. All right. So in other words, if I ask you to do a second fundamental theorem of a calculus, okay, and then they give you this derivative of the integral of this function, and you can think of yourself as like, okay, derivative and an integral, which is antiderivative, they cancel out. I am only left with f of x because I'm replacing t with the function of x. So let's look at the example. This is it's easier to see example than just looking at that. Okay, there's an example. Say you have to find you have to find this. They're asking you to evaluate this. Okay, if you have to do this work, okay, if you have to do this work properly, actually you don't even know how to do this problem, by the way, because you haven't learned this, how to do trigonometry substitution problem. So if you don't know trigonometry substitution, you don't know how to do antiderivative of this function, square root of t squared plus 1, which you're going to learn in your calculus 2 class. Okay, so you cannot just take antiderivative of this because you haven't learned that tool. So you definitely think about the second fundamental theorem of calculus. So you're going to say, okay, since I have a derivative in the front, I have antiderivative in the inside of the derivative. So I can think of they're canceling out because derivative and antiderivatives, they're opposite. Okay, so they're canceling out. They're inverse to each other. So I am left with this. But I want to replace that with what? X. But remember, I gotta take a derivative of x. What's the derivative of x? Just the 1. So it happened to be just the 1. So I can just simply put this into x squared plus 1 minus 0 squared plus 1 and everything times 1. Because 1 is the where you came from, derivative of x. Remember, you gotta take a derivative of this. It says a derivative of your limits too. So derivative of 0 is a 0. Derivative of x is what? 1. So I'm multiplying by 1. So this just equal to 0. So I'm left with square root of x squared plus 1, which is same as x squared plus 1. All right. So now my next question is, if I give you this, then what is the x? Okay. I'm taking a derivative of x. So what is my answer? It's exactly the same problem, but my upper limit changed. Does everybody see it? My upper limit is now x squared. All right, so what it says is, it says if I do derivative respect to x, the parentheses of entire thing, you can think of antiderivative and derivative can cancel out. So I can simply say, okay, I'm going to do this and I'm going to evaluate it, but I also need to do what? Derivative of x squared, right? And then you're going to have a derivative of 0, doesn't matter, it's a constant, so I don't even have to worry about it. So that's what you have. So I'm going to replace it. And then what you need to do is what? Derivative of this. What is the derivative of that? That'll be 2x. All right, so my answer is now that just, oh, that is not 0. Excuse me, I made a mistake. But actually they want you to just change it. Excuse me. So I made a mistake in here. So you're not even evaluating. You just replacing. You just, the formula says you just replacing this. So you're replacing x squared, excuse me, Okay, you are replacing t as x squared. So I have x squared to the square plus 1. And then I have a derivative of this. So which means I have my answer is now x to the 4 plus 1 times 2x. So 2x times x to the 4 plus 1 is your answer. So because you know the second fundamental theorem of calculus, this problem becomes a lot easier for you because you can just simply use the formula. All right, so let's look at another one just in case you didn't get this problem. I'm again using a second fundamental theorem of calculus. So if I have this to say, okay, if they will ask you to do this problem, and you're gonna say to yourself, oh, okay, this means the second fundamental theorem of calculus, so I can use that theorem. And theorem says I can simply replace t with what? Upper bound. All right, so I'm gonna have cosine, but I'm gonna use my upper bound, which is okay, and then what do you need to do? I'm going to take derivative of upper bound. Okay, so my answer is now cosine 3x squared times upper bound. The derivative of that is just the 6x. So my answer is just 6x cosine 3x squared. So I'm done. All right, so anybody have any questions so far? Hold on, let me wear my mask. Wait, do you need help? All right, let's go back. So this one is a mistake, right? We don't need this part right here. So only that one. All right, classes, give me 1 minute. Wait, actually, I wanted to keep this one because they're gonna give me a call today to reset and try it. Okay, so I'll pick it up from you next Tuesday. All right, any questions so far? Is everybody good with the second fundamental theorem of calculus? All right, so now let's look at the net change. Thank you. So net change theorem, okay, net change theorem is just like first fundamental theorem of calculus. Okay, they wanted to know where this integral can be useful, like physical usefulness. So remember, so integral, you learned that the physical usefulness is finding an area under like an obscure curve, you know how to find it. That's the one usefulness that you found as an integral. Now, they're saying, okay, there's another usefulness you can think of as a physical phenomenon. All right, so net change theorem. So in other words, say your function is continuous. Again, the calculus, we always assume function is continuous. If it's not continuous, a lot of things we cannot do. We cannot take derivatives and things like that. So we assume f is continuous in the closed interval a and b. Okay, so now I'm going to say f, again, f is what antiderivative of f. So in other words, I get this when I take antiderivative of this. All right, the function. But now, since we decide to use capital F as antiderivative of f, I can rewrite the f of x as what? F prime of x. All right, let's do that. So it makes sense, even more makes sense. All right, so that means we learned that this is nothing new. This is a fundamental theorem of calculus. So which means I take antiderivative of this, which gives me an original function. And then what do? I plug it in. When I get this, I plug it in A and B, which gives me this. All right, that's nothing new. All right, so that is, in other words, net change. Okay, you get to see it. What is the change between the upper limit to lower limit, the net change? In other words, area under that curve between A and B, it's same as net change. You can think of as net change. You know what net means, right? Net means what is came out of. What's the outcome? What's the last thing you see it? After you do all this work, what is your net? Like thinking of it like money. You earn this much money and you spend this much money, then what is your net? What are you left with? Okay, that's a net. So you can think of this as a net change is same as that, which is same as a first fundamental theorem of calculus. So this is an example problem. Look at this. A chemical flow into a storage tank at a rate of this. This is my rate. So you can think of f prime of x. All right. A liter per minute, where t is a time in minutes, which means 0 to 60 seconds. Find the amount of a chemical that flows into the tank during the first 20 minutes. I want to know, this is a very good problem. So you probably see this kind of problem in your physics class for sure. All right, chemical that flows into a tank during the first 20 minutes. So I want to know the net change between 20 minutes to 0 minutes. So 20 minutes, the chemical is going through the tank. All right, I want to know how much the chemical is in the tank, in other words. Okay, so now I'm going to f of c of t to be amount of chemical in the tank at time t, and c of t is a represent rate which the chemical flows into the tank at a time. They're just using a different letter. It doesn't matter. We've been using it f x, and then we've been using f of x. But now they say, let's use C because it's a chemical. Okay, chemical stands for the C, so they're using a C. So they're gonna use C of T, and then C of prime of T is the rate. And this is the original amount. It's just the amount that you're gonna have. So we're gonna rewrite that problem as a calculus problem. All right, so read this problem again. As a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. They gave you a rate of change. Okay, they give you rate of change. Now, where is t is a time in minutes, which means 0 to, and then t is between 0 to 60. So it's a 0 to 1 minute, okay, 0 to 60 seconds. Find, 0 to liters per minute. So 0 to 60 minutes, which means 1 hour. They want to know between 0 to 1 hour, right? They're using only that as your limit. But now I'm not interested in entire 1 hour, but I only wanted to know up to 20 minutes. So find the amount of a chemical that flows into the tank during the first 20 minutes. So now my lower limit is a 0. My upper limit is a 20. My chemical, the rate of change, how much the chemical flows in, the rate of a chemical flows in is 100 plus 3t. So you simply take a derivative of that, antiderivative of that, you get 180t plus 3t squared over 2. That's what you get. And you're going to evaluate it between 0 to 20. All right. So when you plug it into your number, you get a 180 times 20 plus 3/2 times 20 square minus 180 times 0 plus 3/2 times 0 square, which give you 4,200. So you just figured out, okay? That's why calculus is important. You just figured out. It says, so the amount of a chemical that flows into the tank during the first 20 minutes is 4,200 liters. Okay, without knowing calculus, this problem will be tremendously hard. But because you know calculus, you know fundamental theorem of calculus, because of that, you can figure it out. You said, oh, you know what? That's a simple problem. I just take an integral of this problem, net change problem. So there's, in other words, first fundamental theorem of calculus gave you a power to do, complicated problem like this. Next one. So this is the same thing, another one. So another one is, you can think of distance, okay? So another way to illustrate the net change theorem is to examine the velocity of a particle moving along a straight line where s of t is a position at a time t, and the velocity is vt, which is same as s prime of t. So you can think of that. So this is a displacement. The definite integral represents a net change in position in a displacement. By the way, displacement means it's a net change. So if you particle move to the left and move to the right, you move back and forth have to be same amount. Say, this is a good example. Say if you're starting right here, and then your particle move to the left, so -10. And then your particle move to the right, +10. Where are you now? Where's your particle is now? It's still 0, isn't it? -10 plus +10 give you what? 0. So the net change is a 0 because even though you move to the left 10 units, or you move back to the right 10 units, so your net change is 0. So displacement is, they can cancel out. That's a displacement. So your particle can move to the left, move to the right, move to the left, move to the right. That means you're not actually moving any. When you look at the end of the time, you're exactly the same position. That's a displacement for the particle. But there's another thing. Now, there's net change for the velocity, which means I don't care about moving left and right. I just want to know exactly what's the total displacement. Okay, they call it total distance. Okay, whenever looking for the total distance, you have to think as a absolute value, which means integral, whenever you have this x-axis or t-axis, whichever you want to call it, the bottom part under the t-axis is a negative number. And above the t is a positive number. So if you just look at the displacement, the net change, you cancel out. The negative and positive can cancel out like this over here. All right, so A is a positive, but A2 is a negative because it's under the t-axis. Okay, and A3 is a positive. So when you look at the displacement, you get the smaller number because you cancel out some of them. But when you look at the total distance travel, okay, total distance, which means they want to know, it doesn't matter whether you cancel out or not, I don't care. I want to know exactly how much I travel. Whether I travel to the left, travel to the right, or left and right, it doesn't matter. If I travel, I want to count every distance I travel. That's called total distance. That's your absolute value. So in your case, the second part, even though it's under the t-axis, still you're going to count it as a positive number. So total distance is a larger number. Okay, displacement sometimes can be same as total distance, but the total distance is everything you count, you move. And displacement does not matter. If you move left and right a lot, that means to them, to like end result is you didn't move any. That's a displacement. But the distance means every part that you move, you're gonna count. Say I drive to Little Rock, I came back here. So my displacement is 0 because I came back here, so I'm where I am where I started. That's a displacement. But the distance is, if I drive to Little Rock, that's 35 miles. I came back here, that's 35 miles. So my total distance is 70 miles. Does everybody understand the difference between displacement and total distance? So total distance is how much you travel. Every part that you travel, you're gonna count. And displacement means where you start, where you end, that matters. So this problem is a great problem. So t to the third minus 10 squared plus 29 plus 20. Okay, they were asking you, what is the displacement of the particle on the time interval 1 to 5? And what is the total distance travel by the particle on the interval 1 to 5. So that will give you great answers. Okay, so you're looking at this. So when you're looking for displacement means I don't care whether it's under the x-axis, or under the t-axis. I don't care. Okay. Here's a picture. This is what picture looks like. This one, when you graph that will look like this. All right. So this is what it looks like. Okay. So for displacement, I don't care which one is negative and which one is positive. Like this is a negative. I don't care about that. The sign doesn't matter. That's a displacement. So I'm just simply taking an antiderivative over this, which you get this. And you plug it in, 5 as your upper limit, 1 as your lower limit, and you get this number, and you get 30 or 32 over 3 as your displacement. Now, total distance is different. Total distance is, it matters which part is under the t-axis, okay? So I have to make it into two parts. The part is positive plus, and part is what? Negative. So take a derivative of that part and then that part. So when you get this number which is right here, this number will be negative. But you're gonna make it to be a positive number because you want to add them together. Remember, I'm doing an absolute value. So you have this, okay? So they put a negative in the front. The reason they put the negative is, you know this answer right here is a negative number. So I want that to be a positive number. How can you do that? By doing a what? Multiplying by what? Negative to get a positive number. So important thing is this. When you do total distance, I want you to make it into two parts, where the area is a positive and the area is a negative. And then what do? Whatever the number you get, you just consider everything to be an absolute value, just thinking as a positive number. So when you find this, 1, 2, 4, you get this number, 45 over 4. Okay, when you do this number over here, you get negative 7 over 12. But remember, distance is always positive. So you're gonna make negative 7 over 12 as 45 over 4 plus 7 over 12 and give you 70 over 6 feet. So which means this particle moved 71 over 6 feet, which is a lot more than total displacement. Displacement means it cancel out. The part that you cancel out, I don't care because I want to see a net change. But the total distance means I care about every part, whether you move to the left or move to the down or move to the up. I care about every bit of it. That's called total distance. All right, so that's it for the 4.4. So I want you to finish 4.1 through 4.4, every one of them. And then I'll finish 4.5 tomorrow. And then I can probably review a little more on Thursday. And then you have an exam next Tuesday.